Okay, we continue with our series on animal genetics. And today we'll be looking at relationship and inbreeding in animals. Inbreeding we treated in the last module, and we remember that it is the mating of genetically closely related individuals such as full sibs sharing the same father and mother, half sibs sharing one of the parents, causing matings. Matings from full sibs and half sibs produce inbred individuals. Likewise, parents to their children. So genes from such closely related individuals are said to be alike by descent. And the level of inbreeding in a population is measured by the inbreeding coefficient F, given that F is the sum of half n raised to n bracket open 1 plus FCA. So n is the number of individuals along a particular gene path in a given pedigree. So the FCA is known as the inbreeding coefficient, and for full sibs is 1/4 or 0.25, and for half sibs is 1/8 or 0.125. So if the common ancestor is not inbred, then the formula changes and becomes F equals to sum of half raised to n plus 1. So inbreeding coefficient can also be estimated, particularly in a closed population, using Losch formula, which states that F is equals to 1/8m plus 1/8f, where m and f represent the number of males and females in the population that is being considered. So the rate of inbreeding is affected by the following. It is affected by the frequency of the undesirable genes, meaning that the higher the frequency of such genes, the more prominent is inbreeding in that particular population. The size of the population also affects the rates of inbreeding. Mating within a small population will result in higher level of inbreeding because there are greater probability of related individuals mating together. Linkage between good and bad genes also influence the rate of inbreeding. This is because both the good and the bad genes can easily be transmitted from parents to their offspring. The amount of dominance, epistasis, and the environmental effects also affect inbreeding, but this can be influenced by the decision of the animal breeder. The skill of the breeder is also a big factor. In selection programs, this will require the keeping of records to enhance better decision making. So if the breeder is not very skillful, there is a higher propensity of inbreeding occurring. So prolonged inbreeding in animals can produce the following positive effects. For example, it can lead to the production of pure lines or purebreds. These are genetically pure. It can increase homozygosity in a population, and when there's increase in homozygosity, there's decrease in genetic variability among individuals within such a population. It helps in maintaining relationship of an offspring to an outstanding individual. It results in sorting out of gene complexes. It can concentrate detrimental genes in a family. It also helps in development of uniform lines that become highly adaptable to most environments. The problem with this is that because they are mostly homozygous, they are lacking in genetic variability. Inbreeding can also be used to develop new breeds after a series of crossbreeding, as occur, for example, in the Angora rabbit. However, inbreeding can lead to these negative effects. Generally, all the negative effects occurring due to inbreeding are collectively known as inbreeding depression. And this comes as a result of increase in the level of homozygosity and decrease in heterozygosity, leading to lower genetic diversity. So inbreeding depression manifests itself in depressed growth or growth rate, loss of vigor, low vitality, loss of fitness. It reduces the performance of animals because they become less healthy, more susceptible to diseases. There are possibility of appearance of later genes in the population. It reduces the reproductive performance of animals, especially with traits related to fertility and survival. It leads to slow testicular growth, early embryonic death, and so on and so forth. So we take a look at relationship and inbreeding coefficient. So when an animal is said to be related, animals are related when they share ancestors. It could be one or it could be two. So relationship in this case is either by descent or in state. It is by descent when the genes of the individual are identical. Genes of both parents are identical. So by right, by descent, the offspring will have the same genotype. So this is not by chance, this is expected. However, it becomes a state when the genes of the individuals become identical by chance. This occurs, for example, when two heterozygotes at a locus are mated. So these are two heterozygotes. The possible progenies will carry this genotype to be by chance, and by chance. So all animals that are within a breed are said to be related. For example, all white Fulani cattle are related. And up to 10 generations away, then we can classify them as being unrelated. So the relationships are linked to 5 generations within a family. And the coefficient of relationship is estimated using this formula. And this formula is defined as the Rxy is the coefficient of relationship between animal X and animal Y, and N is the number of generations between the two animals and their common ancestor. And in relationship, the coefficient of relationship values usually range from 0 to 1. And we use what is known as arrowed or pedigree diagram to show the relationship. So let's take a work example. We want to find out the coefficient of relationship between two full sieves and two half sieves. So this is a diagram showing two full sieves coming from parents A and B. And from this diagram, we can see that there are two common ancestors, A and B, and both of them make contributions to the two individuals, X and Y. So because there are two common ancestors, there will be two gene parts. This is one gene part, and this is another gene part. One coming from each of the ancestors, A and B. So let's recall the formula for estimating relationship. So if we apply that to the full sieves, we'll see that it's making two contributions, one to X and one to Y, one to X and one to Y. And if you run it, this gives us half raised to power 2 plus half raised to power 2, and this will give us 1/4. 1/4 plus 1/4 is give us half. So the relationship between two full sieves is 0.5. What of two half sieves? Half sieves are produced when two individuals share one common ancestor. A is a common ancestor, B is the mother to X, and C is the mother Y. So X and Y are half sieves. Here, because there's only one common ancestor, therefore it is only it that is making contributing common genes to X and Y. And because of that, there will be only one gene part. So recall again the formula for coefficient of relationship. And because there's one gene part, we can only have N1 plus N2. And if you got that, it's one quarter. So the relationship, coefficient of relationship between two half sieves is 0.25. And you should recall this is half of the relationship between two full sieves. So we want to calculate inbreeding coefficient when the common ancestors are not inbred. The formula changes to Fx sum of half ns plus nd plus 1 bracket open 1 plus coefficient of inbreeding coefficient, where the ns and nd equals the number of individuals along the gene path from the sire to the dam. So, as an example, let's calculate the inbreeding coefficient of the product of mating between two full cousins. So, Q and Y are the common ancestors. They give birth to full sieves, M and N. N gave birth to S, and M gave birth to D. So, S and D are full cousins. And you want to know the inbreeding coefficient of the product of mating between S and D. So, because the common ancestors are not inbred, the coefficient of inbreeding coefficient is 0. However, we have two gene parts since there are two common ancestors, X and Y. So, if we apply that into the formula, that Fs is equals to half Ns plus Nd plus 1 for Q and half Ns plus Nd plus 1 for Y. You will have this. There are two gene parts between Q to the cousins that are going to mate. So that's why we have there two gene parts from the sire and two from the dam for Q, two from the sire and two from the dam for Y, plus 1. That is half raised to power 5 plus half raised to power 5. And if you solve that, it will give you half raised to 32 plus half raised to 32. And the final answer is 1 over 16, which is 0.0625. So that is the inbreeding coefficient as a result of mating between two full cousins. Now, what of if there are two full half cousins? So they have a common ancestor, the sire. A is a dam, B is a dam, giving birth to N. This and this gave us M. So these are half sieves. And when they produce their own offspring, S and D are half cousins. And if they mate, the product is X. So we want to calculate the inbreeding coefficient as a result of half cousins mating to produce X. Now, because they are half cousins, they only share one common ancestor, which is C. So again, only one gene part will be done here. And C is not inbred. So because of that, the inbreeding coefficient is equal to 0. There's only one gene part necessary. Okay, this is a mistake. It's supposed to be from C. It's supposed to be from C. So, therefore, the formula changes to this. And if we do that, it's going to be half 2 plus 2 plus 1, and then that will be half raised to the power 5, and that will be 1 over 32, or 0.03125. But what of if this calculation is for half sieves and not the half cousins? So this is dam A, the size is B, and C another dam. These are the parents, and these are the half sieves. Our interest is in their progeny. So again, this will require only one gene part. So the formula will only run through one gene part. And there we have half plus 1 raised to n from the sire 1, from the dam 1 gene part plus 1. This is half raised to power 3, and that is 1 over 8, or 0.125. But let's now try to calculate inbreeding coefficient when the common ancestor is inbred. Initially, we're looking at inbreeding coefficient when the common ancestor is not inbred. So, again, this is A is a dam, B is a sire, and C is a dam. So these are their offsprings that are half sieves. So when the two half sieves mate, they produced another offspring, which is F. F is inbred because half sieves left to its production. So if the inbred ancestor mated with G and H to produce I and J, we want to calculate the inbreeding coefficient of K, which is the product of the mating. Let's be mindful that F, the inbred ancestor. So the common ancestor to both the common ancestors to both I and J are F, G, and H. So we are going to calculate to get their contribution to the inbreeding that is occurring within the product of the mating. So the gene parts that are available from that chart are I, G, and J, and there are 3, 1, 2, 3. These gene parts do not have any inbred individuals, so the inbreeding coefficient is 0. And if you put it into the formula, half raised to power 3 bracket 1 plus 0 will give you 1 over 8. IHJ also 3 gene parts, no inbred individual there. It will give you 1 over 8. Or if you take the gene part IGFHJ, there are 5 individuals within that line. And remember that F is inbred. And in that case, the inbreeding coefficient is 1 over 8 because F is produced from half cousins. So that will be half raised to power 5, bracket open 1 plus 1 over 8, bracket close. If you do that, it will give you 9 over 256, which is 0.03516. Again, I, H, F, G, and J. F, again, remember, is inbred. It was produced as a result of mating between two half sieves. So the inbreeding coefficient for half sieves is 1 over 8. Again, if you solve it, it's 9 over 256, 0.03516. So n is the number of generations along the gene paths, and when we add up this to this, it gives us an answer of 0.3203, or 32.03%. So because there's a common ancestor along the gene path, that common ancestor, it led to an inbreeding coefficient of 32, about 32.03% inbreeding in that population. So we can now see that there's a relationship between inbreeding and So there's a relationship between inbreeding and relationship in animals. The closer the relationship, the higher the inbreeding coefficient, and the wider the relationship, the lower is will be the inbreeding coefficient. I hope we have learned something pertaining to this relationship, and we can actually use it when we are carrying out the breeding program in order to limit the amount of inbreeding that will occur in a particular population because of the inbreeding depression that will set in and with its negative implication. So thank you for listening. Uh, don't forget to subscribe, to make comments, and to share to your friends. And wait for our next video.